Hello everyone, I am Sravani Konda, a technical consulting engineer at Intel. In this presentation, I will be talking about our joint collaborative work with AMReX developers Wei-Chun Zhang and Kevin Gott and share our experiences in supporting Data Parallel C++, or popularly known as DPC++, a language based on the SYCL specification as a backend for AMReX. I would also like to mention my colleagues from Intel, Dunia Ribuki and Christopher Lishka, who are part of this effort. In this talk, we present an overview of AMReX, how AMReX provides an abstraction layer for its users so they can write performance portable code for a variety of heterogeneous platforms. We will discuss key DPC++ features that allow AMReX to implement the abstractions and our contributions to the OneAPI specification and Intel's implementation. We will also highlight some features missing in SYCL and DPC++ that limits AMRex's efficiency and the current status of the DPC++ backend. The picture on the right here is a snapshot of the instantaneous flow field for an NM80 rotor using the hybrid EXA wind simulation solver suite for wind energy. In wind farm simulations, a small fraction of the domain needs unstructured grids, but a vast majority of the domain can be discretized with structured grids, which is done by AMReX-based AMR Wind code. Here's an overview of AMReX. AMReX is a software framework designed for building massively parallel block-structured adaptive mesh refinement applications. It is developed at Lawrence Berkeley National Labs, National Renewable Energy Lab, and Argonne National Lab as part of the Block Structured AMR Co-Design Center in the Department of Energy's Exascale Computing Project. AMReX has C++ and Fortran interfaces, and its main capabilities include subcycling in time for time-dependent partial differential equations, support for particles, embedded boundary representations of complex geometries, linear solvers, and parallel and asynchronous I/O. AMReX uses the model of MPI plus X for parallelization, where X can be OpenMP, CUDA, HIP, and now DPC++, and is run on a variety of machines from laptops to supercomputers. AMReX is used by a large number of applications in the US national labs, academia, and industry, including the ECP projects ExaSky, ExaStar, ExaWind, MFIX-Exa, Pele, and WarpX. In addition to this, AMReX is also being used to develop software tools in the community, such as for testing the HPC toolkit on pre-exascale hardwares, Tulip and Iris, and for Intel performance tools testing on Iris and Intel Dev Cloud. Currently, high-performance computing is in an era of heterogeneous computing of CPUs and GPUs. AMRex's main supercomputer targets are some of DOE's machines like Summit, Perlmutter, Frontier, and Aurora. These have different architectures and require different programming models. AMReX writes platform-specific code using CUDA, HIP, and SYCL or DPC++, so users can write performance-portable applications targeting these different architectures. Now let's dive into the technical details of AMReX and start off with the basic data structures of AMReX. At the core of the AMReX software is a flexible set of data structures that can be used to represent block-structured mesh data in a distributed memory environment. Multi-level data on the AMR grid hierarchy are stored in a vector of single-level data structures. Grids with the same mesh spacing are disjoint, and the union of such grids is referred to as a level. The example we are looking at here is a 3-level grid. The primary data structure for AMReX mesh-based work is a container called multifab, which is a collection of box arrays at a single level. Most applications use it for storing floating point data on single level grids, but can also be used to store integers, complex numbers, or any user-defined data structures. It also contains a distribution map defining the relationship across MPI ranks. Each box's data are in a multidimensional array called F-array box or fab. A fab contains the box that defines its valid region and a pointer to a multidimensional array. For three-dimensional calculations, the data accessed by the pointer in a fab is a four-dimensional array, where the first three dimensions correspond to the spatial dimensions and the fourth dimension is for components. AMReX provides an accessor array 4 that can be used to access the data in a fab or other similar objects. This class does not own the data and is not responsible for allocating or freeing memory. It simply provides a reference to the data. This property makes it suitable for being captured by a C++ lambda function and passed to a GPU device without memory management concerns. AMReX provides a data iterator called MFIter to loop over the boxes in a multi-fab or fab array with the option of logical tiling. The iterator can be used to access data from multiple multi-fabs or fab arrays built on the same box array with the same distribution mapping. The example here shows 5 boxes and kernels are launched on each box. The CPU flow is represented by the arrows here, and after it finishes launching all the kernels, it calls device synchronization. For GPU, in case of DPC++, we used ordered queues as it's a simple way to maintain order for computations on the same box. The benefit of asynchronicity is obtained with multiple ordered queues. To isolate application code from the nuances of a particular programming model, AMReX provides an abstraction layer consisting of several parallel for looping constructs, which are tailored to the needs of block-structured AMR applications. Users provide a loop body as a C++ lambda function that defines the task to be performed over a set of cells or particles. The lambda function is then used in a kernel with a launching mechanism provided by CUDA, HIP, or DPC++ for GPU or standard C++ for CPU. The details of how to loop over the set of objects, and in particular how to map iterations of the loop to hardware resources such as GPU threads or execution units, are hidden from users. By separating these details from the loop body, the same user code can run on multiple platforms. In addition to 1D loops, users can also specify 3-dimensional and 4-dimensional loops as shown on the right by passing in the box argument as the loop bounds. The parallel for relies on C++ lambda and captures the trivial non-owning pointers a and b. Internally, the parallel for construct is implemented using SYCLparallel for the DPC++ backend. AMRex's parallel for is portable on CPUs and different GPU devices. Parallel reductions are commonly needed in scientific computing. For example, in an explicit hydrodynamic solver, one needs to calculate the time step by examining the CFL constraint in each cell and then finding the minimum over all cells. Similarly, in linear solvers, one needs to measure norms of the global residual. Performing reductions efficiently in parallel in a way that is portable between CPU and various GPU platforms is non-trivial. So AMReX provides generic functions for performing reduction operations in a performance-portable way. These functions can be used at the level of contiguous arrays by passing in data pointers, or they can work on higher level AMReX data structures to perform reductions over all the cells in a multifab or all the particles in a particle container. One of the features of the AMReX implementation of parallel reduce is an API for performing multiple reductions in one pass using a reduced tuple data type, which is shown in the example here on the right. The code in this snippet shows we can launch just one kernel per box to compute min, max, and sum of all the real data in a multifab. Given AMRex's needs of performing reductions on set of multidimensional arrays, the high-level SYCL reduction APIs for one-dimensional arrays does not work. However, the DPC++ subgroups extension, particularly the subgroup primitives like shuffle down, up, and XOR, have enabled AMReX to write efficient parallel reduction and scan functions. So here's an example of the code generated by the DPC++ backend for an AMReX-based application code on the left. Application is using AMReX provided multifab data containers, Iterator MF iter, and AMReX parallel for to launch a kernel performing a user-defined computation, which is captured as a lambda. AMReX backend for this is generated by creating an ordered queue using SYCL's kernel launching mechanism of submitting the job using SYCL parallel for over ND range, where the total number of threads to launch and threads per block here are computed from the box. The error handling here is done using SYCL's try-catch error handling mechanism. The effort to add the DPC++ backend to AMReX started in early 2020. Having some of the extensions as shown here, which are now available in SYCL, has been instrumental in supporting major AMReX functionality in the DPC++ backend by the end of 2020. The first one is unified shared memory, which provided the flexibility and it fit naturally with other AMReX backends. Second is ordered queues. Most of the operations in AMReX are naturally ordered, and we're using streams in CUDA and HIP backends, so in-order queues were handy to recreate that functionality in the DPC++ backend. Subgroup shuffles and collectives allowed AMReX to write custom reduction and scan operations effectively. Next is the host task callback. So AMReX has something called SYCLarray, which is a dynamically sized array container designed to work between the CPU and GPU, which stores a CPU pointer and a GPU pointer and coordinates the movement of an array of objects between the two. A host task to delete this memory is enqueued on an ordered queue in the destructor of SYCLarray, which guarantees the memory allocated continues to exist after the SYCLarray object is deleted when going out of scope until after all the GPU kernels in the stream are completed, without forcing the code to synchronize. Next are divide-wide memory fence. This feature has been useful for synchronization in parallel scan and similar functions and to achieve code correctness. In addition to these language-specific features, some other extensions of one API that have been extremely useful to AMReX are C++ standard library support in DPC++ and the 1MKL library. So the C++ standard library support in DPC++ enable the usage of C and C++ functions such as math functions from the std namespace in device code. This saved time from modifying existing usage of these in our device functions. And the 1MKL library of an API provided functionality to use random number generation and multidimensional fast Fourier transforms in AMRex's device code. So here are some language and specification influences we've been able to make from this effort. AMReX, as part of its memory management, required to know the amount of free memory available in the device. This request motivated to update one of the low-level APIs in the level 0 runtime, which was previously returning only allocated memory, to instead return free memory, which is more actionable for a user. The device info interface returns a set of subgroup sizes supported by the device, but only one size may support all the core language features for the device. So we requested to have a primary subgroup size to get this, which has been accepted into Intel's subgroups extension. Next, it is sometimes inconvenient to get the current ID, ND item, or subgroup instances way down the call chain in device functions. So we advocated for free functions for these, which are now available in DPC++. We also worked with the 1MKL specification owners on the device random number generation APIs as one of the first customers for this API and provided early feedback in their design. In the initial days, when support for STD absolute function wasn't available in device functions and we were using the SYCL absolute, we observed that the return value is incompatible with the C++ or CSTDLib versions, where the SYCL absolute returns unsigned int instead of signed int. We reported this to Intel, and we believe that representatives from Intel have brought this to the spec's attention. And here are some product-related influences that we've been able to make, especially to the DPC++ compiler. One of the AMReX-based ECP applications, WarpX, requires support for recursive functions in device code, which wasn't initially supported by the DPC++ compiler. Our feature request for this was accepted and it is now supported. Next is the assert in device code. The current implementation of device code assert in DPC++ compiler only dumps assert information to std error on host after kernel execution. The application continues running and the user code isn't notified about the assert failure. So we requested for the compiler to throw an asynchronous exception upon detection of device-side assert, which is currently being worked on. Next is the DPC++ kernel argument size limit. So low-level APIs like OpenCL, CUDA, or Level 0 have limits on the kernel parameter size, as these parameters are passed by value and usually via registers. AMReX was used to CUDA's 4 KB limit here, and with a 1 KB limit in DPC++, we were often hitting this limit for kernels with large arguments. The situation was improved later by optimizing the way the compiler captures the kernel arguments and also increasing the limit to 2 KB, which covered most of the use cases for AMReX. Next is querying the device UUID. So in order to enable MPI with DPC++, we need device universal unique ID or UUID for each GPU or device, which helps with getting the total number of unique devices and assigning MPI ranks. This information is available in low-level APIs like Level 0 and OpenCL, so work is in progress to add it to DPC++ and possibly to SYCL device info in future. Now let's look at a couple of features that are missing in DPC++ and SYCL and are limiting the efficiency of AMReX. The first one is local memory in device code. It is sometimes inconvenient to use local memory in device functions down the call chain, as it requires the object or pointer to be passed all along to where the local memory is used. Here's an example on the right showing how the device function transpose needs local memory shared across kernel instances or threads and can be easily achieved using the shared keyword in Konda. There is no such functionality available in SYCL or DPC++ today. We are currently working around this issue by creating a local accessor outside the kernel and capturing it, but we would like to see a cleaner way of doing this. Intel's extension proposal for local memory addresses this concern to some extent of being able to allocate local memory, but it still has a restriction that the group local variables must be defined at kernel functor scope. Next is global device variables. Many AMReX applications have the definitions and declarations of global variables spread over different files or translation units, and these are used on the device to communicate between multiple invocations of the same kernel or between kernels. We would like to see support for accessing the global variables in device memory, and particularly a memcopy function for copying this data from the host to the global variable, which is currently supported by both CUDA and HIP. As shown in the example here, declaring the global variables as OpenCL constants helps with accessing them in device code, even in CUDA, HIP, and SYCL, but the functionality to copy data to these variables from the host, which is often from a different compilation unit, is missing in SYCL. AMReX had to re-implement its random number generation API to work around the need for a global device variable that is implemented such that users are unaware of it. So here's the current status of the AMReX DPC++ backend. All major capabilities such as mesh, particle, embedded boundary, linear solvers, parallel reduction, and random number generation are now supported. There are extensive tests and tutorials in AMReX which were tested with the DPC++ backend and work as expected. ECP codes such as MFixXR, Warpx, Nix, AMRWind, and PeleC have successfully run some of their workloads with DPC++. We are working with AMReX users from ECP and broader community to prepare and achieve scientific excellence on upcoming Aurora. To summarize, AMReX has chosen DPC++ as its backend for Intel GPUs and successfully ported all major capabilities with the power of C++, SYCL, and DPC++ extensions. DPC++ has enabled us to create an abstraction layer between the platform or architecture-specific backend and the application, and this provides existing AMReX codes with performance portability to run on Intel GPUs. This collaboration enabled identifying several limitations in the language and DPC++ compiler, thus improving them for the benefit of the larger community. AMReX is looking forward to running on Aurora and other Intel GPU systems using DPC++ and also testing its cross-platform capabilities on NVIDIA and AMD GPUs. Lastly, we'd like to thank Intel Dev Cloud and Argonne National Labs' JLSE for providing the resources for development. Thank you for the opportunity to share our experiences with DPC++ and AMReX.